Here is a combined summary of the 2 pages. The proposed approach, selective debiasing, aims to increase the overall quality of models in terms of prediction performance and fairness in situations where model retraining is prohibitive. Inspired by selective prediction, this method identifies potentially biased model predictions and debiases them using a post-processing debiasing method, such as LEACE. A bias quantification approach based on KL divergence is used to select problematic predictions, achieving better results than standard uncertainty quantification (UQ) methods. Fairness is a critical safety characteristic of machine learning models, representing the model's ability to classify instances without discrimination based on sensitive attributes. Group fairness, also known as the equal opportunity criterion, reflects the inequality of opportunities across different groups. Debiasing techniques can be categorized into 3 groups: at training, preprocessing, and post-processing. Post-processing techniques, such as LEACE and INLP, do not involve changes to the model itself and can be applied to predictions selectively. Selective debiasing combines the benefits of post-processing debiasing and selective classification. Instead of rejecting predictions of selected instances, the approach applies debiasing to them using a post-processing method. This approach modifies only a subset of predictions, reducing the risk of worsening the overall performance. The main contributions of this work include proposing selective debiasing as an inference-time safety mechanism and a scoring criterion to select the most unreliable and biased predictions. Experiments demonstrate that selective debiasing helps to close the performance gap between post-processing methods and at training and pre-processing debiasing techniques. The approach allows for flexible adjustment of the accuracy-fairness trade-off by applying debiasing to only a selected subset of predictions. The bias quantification method based on KL divergence outperforms UQ methods in selective debiasing, illustrating the need for a different selection criterion to improve fairness without penalizing accuracy. The proposed paper presents a novel approach to enhancing model fairness and accuracy, known as selective debiasing. This method is designed for situations where retraining a model from scratch for better fairness is not feasible or when there is no access to the full training data. The approach utilizes Kullback-Leibler (KL) divergence to quantify bias in predictions, leading to improved results compared to the standard uncertainty quantification (UQ) method. In the experiments, the authors compare various debiasing methods and selective debiasing techniques using LEACE and INLP. They also compare different bias quantification methods such as Euclidean and cosine distances. The results show that the proposed selective debiasing method significantly enhances fairness and accuracy, particularly in the case of the MOJI dataset, and is competitive with the training and preprocessing debiasing techniques. The proposed KLBASED bias quantification method outperforms the SR method on MOJI datasets and is on par with SR on BIOS2. The paper highlights the potential of the proposed method to fill the gap for efficient techniques that can be applied at inference time, opening the door for safer MLBASED systems. The future work aims to investigate a deeper integration between UQ and debiasing methods. This research focuses on group fairness, specifically the equal opportunity criterion, and instance-level bias quantification. The authors acknowledge limitations, including the assumption of access to protected attributes, which is necessary for fairness metric calculation, and the language dependence of the experiments, although the methods are language independent. Ethical considerations are addressed by using publicly available datasets and models, and only applying debiasing methods to attributes self-disclosed by users. The authors cite various studies on bias in NLP, including language technology, demographic dialectal variation, and semantic representation bias. They also reference works on debiasing methods, such as perfect linear concept erasure, selective classification, and adversarial training. The importance of uncertainty estimation for debiased models is highlighted, as well as the need for robust and privacy-preserving text representations. The authors draw on research on fairness without demographics through adversarially reweighted learning, and the use of pre-trained language models like BERT and BER-Tweet. They also cite studies on evaluating debiasing techniques for intersectional biases and balancing out bias through balanced training. The authors emphasize the importance of considering multiple fairness definitions and the need for future work on debiasing methods that do not rely on protected attributes. The referenced papers provide a comprehensive understanding of the current state of research in NLP bias and fairness, highlighting the complexity of the issue and the need for continued exploration of novel debiasing methods and evaluation techniques. This research paper presents a comprehensive evaluation of various debiasing methods for NLP tasks, focusing on fairness and accuracy improvements. The authors use BER Tweet and BERT models on Moji and BIOS 2 datasets, respectively, to assess the effectiveness of different debiasing strategies. They employ a grid search to find optimal hyperparameters for standard models and debiasing methods, with results presented in tables 2 and 3. The overall computation statistics are provided in Table 4. The paper's main findings are summarized in Table 5, which compares debiasing methods and selective debiasing. It is evident that debiasing methods significantly improve fairness and accuracy, with the best results achieved by LEACE with KL score and optimal percentage selection. The results also indicate that using debiasing methods can lead to better performance than standard models, especially when combined with selective debiasing. The study also explores the use of various similarity measures for selection strategies, as shown in tables 10 to 12. The comparison highlights that KL scores perform comparably or better than other distance-based measures, while being easier to compute. In addition, the paper provides detailed statistics for the synthetic dataset used in the experiments, including fairness, accuracy, DTO, and FF score, as well as the optimal percentage of selection for each dataset method pair in Table 9. The paper concludes by discussing limitations and potential future work, emphasizing the importance of understanding how debiasing methods interact with different models and datasets. The research paper presents a comprehensive analysis of debiasing techniques for mitigating bias in machine learning models, focusing on the LEACE and INLP methods. It evaluates these methods across different datasets, including Moji and BIOS 2, which are imbalanced and balanced datasets with attributes like race and gender. In Table 6, the FF scores of selective debiasing for LEACE on the last layer are presented, showcasing how various percentages of debiasing affect model performance. For instance, in the Moji imbalanced dataset, the FF score increases as the percentage of debiasing increases, peaking at 74.3% with 15% SR debiasing. Similarly, Table 7 highlights the FF scores for LEACE on the classifier level, demonstrating similar trends but with varying optimal percentages for different datasets. Tables 10 and 11 compare the FF scores of distance-based scores for LEACE and INLP, respectively, on both the last layer and classifier level. These tables emphasize that different debiasing percentages yield varying improvements in fairness and accuracy trade-offs. For example, in the BIOS 2 imbalanced dataset, the FF score reaches its peak at 94.7% with 15% KL debiasing for LEACE on the last layer. Finally, Table 13 provides an overview of the dataset statistics, including the number of classes and attributes, as well as the train, validation, and test sizes for each dataset. This information is crucial for understanding the context and limitations of the experiments conducted. Throughout the paper, the authors use various metrics such as FRAUC, ACC-AUC, and FF score AUC to measure the quality of their debiasing strategies. These metrics are essential in evaluating the effectiveness of debiasing techniques in achieving fairness without compromising accuracy. The study concludes that optimal debiasing percentages can significantly enhance fairness and accuracy trade-offs, depending on the dataset and debiasing method used. The research paper presents two datasets, BIOS2 and Moji, focusing on gender and ethnicity in the context of emotion recognition. It provides a detailed analysis of the joint distributions for both datasets, highlighting the distribution of gender and ethnicity across different emotions. In the BIOS 2 dataset, the joint distribution for gender and profession is presented in Table 14. The table shows that in the training set, 53.34% of nurses are female, while only 5.74% are male. Similarly, 35.42% of surgeons are male, with a smaller percentage of 5.50% being female. This imbalance is consistent across validation and test sets. However, when the data is balanced, the distribution becomes more even, with approximately 50% of each gender in both nurse and surgeon categories. The Moji dataset, as shown in Table 15, exhibits a similar pattern for ethnicity and emotion. In the training set, 40% of South Asian (SAW) individuals are associated with sadness, while 10% are associated with happiness. For African American (AW) individuals, the opposite is true, with 40% associated with happiness and 10% with sadness. Again, this imbalance is consistent across validation and test sets, but balancing the data leads to a more even distribution of 50% for each ethnicity and emotion combination. These findings indicate significant imbalances in both datasets, which could potentially lead to biased models if not addressed. The use of balanced datasets helps mitigate these issues, ensuring that the model is trained on a more representative distribution of gender and ethnicity. This research contributes to the ongoing discussion on fairness and bias in machine learning models, emphasizing the importance of dataset balancing to promote equity in emotion recognition tasks.